Okay, so welcome to module number 8 in the Pawsey user training series on job scheduling overview. This is module 8 out of 11 of this training series. Among the outcomes for this module are a discussion of what a job scheduler and why we're using it, and how to query the fundamental aspects of a scheduler setup on a supercomputer, so scheduler partitions and crucially job queues. This module is tightly connected to the previous one on accounting of resources and allocations. Watch out for these signs over the session. They highlight key callouts for the topic. So the Slurm Scheduler at Pawsey. In the previous session, we talked about a supercomputer being a shared infrastructure. So how we define an accounting model to measure usage of resources. Now we make use of computer locations to partition available computer resources across the user base. The missing bit is the job scheduler. Before even talking about that, so what is a job? I mean, this is just a small piece of jargon that is important just to clarify. When we say job in this session, in the next sessions, I'm going to refer just to a unit of computational work, piece of computation that needs to be executed on a supercomputer. This is the fundamental unit because that's the one that gets to be managed by the scheduler. So a job scheduler is just a program that manages the queuing and execution of the jobs that multiple users submit for execution on a shared resource, on a shared compute resource. So I'm gonna mention these two terms quite a lot over this module. So the scheduler technology we use at Pawsey, it's called Slurm, provided by a company called ShedMD. As we saw in module 1 of this series, the login nodes are those used to log in the machine and to submit the jobs for execution to the scheduler, but the actual execution happens on the compute nodes. And it's very important not to run anything computationally intensive on the login nodes. And that's actually a matter of good citizenship, I'd say, because as we said, we are in a shared infrastructure. We want the login nodes to be able to be used by all users for what they're designed, which is a lightweight task such as administration of files and directories and setup and submission of job scripts. Login nodes are not designed for running any computationally intensive task. That is the task of the compute nodes. How is a job scheduler useful? So now think for a moment about a weekly planner. So a piece of paper where you have on one axis you have the days of the week, and on the other axis the hours of the week, and then you start and fill it up with various tasks and activities that you need to carry out for the week. And some of them will be short; they will just last for 1 hour. Others for half a day, and maybe some of them will be with a family member, others with a friend, others with work, and then you get to fill up the whole planner. So now think of substituting, of keeping the hours of the day, but of substituting the days of the week with compute resources. So with a list of available compute nodes. And we kind of have what the scheduler has to deal with on a supercomputer. So now the color bars represent jobs that need to run for longer or shorter time. They need to run on one compute node or on 10 compute nodes or 100 compute nodes. And all of these color bars are submitted by different users with different durations and size of the node requests. And then it's a scheduler job to try and fill up this planner as much as possible to maximize utilization of the resource. And so to make sure that the researchers can get their answers out as soon as possible. And in doing that, the scheduler will also take into account what are the available compute resources for each researcher, and it is based on the available on the awarded allocation and on the level of utilization over the quarter, as we saw in the previous module on accounting and allocations. And so let me cover this specific aspect a bit more because it's quite important to highlight. So the scheduler tries and fill utilization of the machine. Oh, that's quite important. So yeah, with this in mind, knowing that the scheduler tries and fill in the slots in the week over the week of a supercomputer. Keep that in mind when planning your work. So if you can maximize the automation and scripting of your job and submit your computational jobs in advance, you will put the scheduler in the best position to best schedule your jobs, and you are more likely to have them running sooner rather than later. So it's good to enter into this habit of having the scheduler as kind of your assistant. It will take care for you of trying to start and execute the job in the best time possible. So that should make you think of making the best use of scripting of your work and automating the execution of your workflows as much as possible. So we were saying the scheduler assign fills in the slots in the planner for the supercomputer for Septonics. Because there are many users that want to use the resources at once, and normally there are more requests than available nodes, the scheduler has to make a choice. Which jobs by which researchers it should have to get started first. And so there are a few aspects that are used by the scheduler to make this choice. One is usage relative to the allocation. So the priority of your job will decrease as the allocation for the quarter is used up. The other one is waiting time in the queue. So as your job waits in the queue, the priority will increase in time slowly. Because we want people to be able to run the jobs eventually at some point. The size of the job is also taken into account, so the priority increases with the size of the job request, so the number of cores and nodes requested. And finally, there's also a fourth factor called the quality of service level, which takes into account a couple of extra aspects. And let's have a look at these. So the quality of service level is just a modifier to the priorities that the scheduler assigns, and how are these priorities modified? So the default quality of service is what every job gets by default, while your quarterly allocation is not used in total. So when you are between 0% and 100% of your quarterly allocation in terms of usage, you get the default quality of service. So there is no modifier applied to the priority. But when you exhaust your allocation, you are between 100 and 150% of usage, so you are overusing it. The quality of service will lower to a lower level, so your priorities will get a hit, and that's again to ensure fair usage of resources by all researchers having access to the machine. And when you are over 150% of the allocation, you will get to the exhausted quality of service, which will mean that your jobs are not able to run until the next quarter, and that's again to ensure fair share usage of the machine. There are also some positive modifiers. So there is a high quality of service that can be self-selected by users using a scheduler option. We're going to cover that in the next module on running jobs. You can use the high quality of service for up to 10% of your quarterly allocation. This can be quite good for jobs that need to be completed urgently, so that we guarantee a bump in priority to these jobs. And then there's also highest quality of service, which is only reserved for critical work, and this needs to be requested with a good motivation via the help desk. So it's only the Pawsey staff that can grant this highest QoS to a user job. So same of allocations, it's important to know that similar as the allocations, quality of service levels get reset each quarter when your allocations get reset as well. Okay, we talked a bit about how the scheduler works and how it is useful in general. Talked about job priorities and filling up the planner and QoS. Now let's talk about another aspect of the scheduler, which is just some jargon, classes and partitions. So within Slurm, there is a definition of cluster, which is a set of compute resources, compute nodes that are all managed by the same Slurm program. It can seem a bit abstract and vague. So in practice, at Pawsey, each supercomputer, so currently we have Septonics, which is the main supercomputer, and then some legacy one, Topaz, Garagola. Each supercomputer has got its own Slurm cluster. The key piece of information is that each Slurm cluster is subdivided in partitions. And now have a look at this sketch of the compute nodes here on the right, the yellow blocks. A Slurm partition is just a subdivision, a subset of resources which have a dedicated queue of jobs. And so the queue of jobs is where the jobs you submit actually get to sit until they're executed. Slurm allows to partition the full cluster in subsets. And that can be helpful and useful. And we're going to see in the next few slides how this is used at Pawsey. So imagine that each of these subsets or partitions of nodes gets its own dedicated queue of jobs for running. So in Septonics phase 1, we currently have 6 partitions of the system. The work so unless specified, keep in mind that the partition would have 128 cores per node, 130 gigs of RAM available, which means 1.8 per node, and 24 hours maximum runtime. Some of them will have different specs. They are outlined. They will be outlined here in the text. So the default partition is the work partition. It has 300 nodes, just over 300 nodes. That's the one. That's the default one. That's the one to be used for regular compute jobs. So that's a standard one if you don't have any specific needs. There is then a debug partition, which is made up of the same type of compute nodes, but it's much smaller. It's 8 nodes. It is used for compiling. Can be used for compiling, benchmarking, and testing. And I forgot to put here that the key feature of the debug partition is that it has a maximum runtime of only 1 hour. So the turnover of jobs is faster, but that's because the purpose of the partition is just testing and compiling. So not production jobs, just preparation and setups. There is then the high memory partition, again, 8 nodes, which feature a much larger RAM capacity. So it's useful for jobs that require more than 250 gigs of memory per node, up to 1 terabyte, and that's what's available. Actually, slightly less, 980 gigs of RAM per node, high mem partition. Then there is a long partition, again, 8 nodes, which and its main feature is that the maximum runtime is 4 days. So this is useful if you have a job that cannot really run within 1 day, which is a default on the work partition. And finally, there is the copy partition. Will be 8 nodes when the system is fully deployed. This is the one to be used for data transfers to and from Septonics. So this is basically the data mover nodes that we talked about in a previous module on moving data. And so the key usage here, it's only reserved for transferring data to and from Pawsey, and actually also within the different Pawsey storage infrastructures. And finally, there is the ASCAP partition, which is about 200 nodes. And this is reserved just for spatial radio astronomy projects related to the ASCAP radio telescope. And so imagine the scheduler at Pawsey on Septonics has got these 6 partitions. And every time you submit jobs for execution, you will pick or default to one of these partitions. So that will, as you will see in the next example, that will be the key point of interaction with the scheduler. So let's have a look at what these partitions look like from the terminal after this presentation slide. So I'm back on the terminal on Septonics. So there is a Slurm command called SInfo that provides high-level information on the various partitions on the system. It tells you basically, will tell you which partitions are available, how many nodes are in use, how many nodes are available, and the node status in general. This is what the output looks like. And you recognize here, these first lines start, if you have a look at the partition column, these are all nodes related to work partition. We have the long partition here, and so on and so forth, copy partition, and so on. Another important column here is the state column that tells you what is the state of the nodes. And that's why, say, for the work partition, there are many lines and not only one. Some nodes are reserved, for instance, for this training that is happening today. Some nodes are down. They're currently unavailable. Some nodes are in maintenance, so unavailable due to maintenance works. And some nodes are in mixed use, which means that only a fraction of the cores in those nodes are being used, others are idle. Some nodes are allocated, which means they're in full utilization as we speak. And another recurrent state, which we can find, for instance, in the copy queue, is idle. So some nodes that are not being used at all right now. So this gives you an overview of the Slurm partition on Septonics. Doesn't tell you, however, anything about the jobs that are running. Just telling you what the status of the compute resources is. This is just the output that we just discussed. Let's now query the specific partitions, and more specifically, the job queues that are related to each partition. And we're going to do that using the command sq. So let's run the command sq. Oh, it's a very long output. So this is the full list of jobs that are currently scheduled on Septonics over all the partitions. You see by default, there are some key pieces of information given. So this is an output by job. So this is telling, this allows you to look for and retrieve information on a job by job basis. So the single pieces of computational work being executed or planned for execution on Septonics. First column is the job ID. Then the second column tells you in which partition the job will execute or is executing, the name of the job, the user who submitted the job, the status of the job. This is quite important. So R means running, the job is running. PD means pending, so it's waiting to run. The time is the elapsed time since start. So this running job has been running for 4 hours, 39 minutes. Then there is a column saying the number of nodes being requested. Beware a number of nodes, not of cores. So you can get the information of the cores, but it requires additional options. By default, only the nodes count is given. And then there is a node list column. So for running job, this will tell you which nodes are being used by the job. For pending job, this will tell you the reason why the job is not running yet. Then there are some handy options for SQ, such as SQ me -- me will just print the jobs that I have queued myself, and there's none right now. I have nothing running. You can also query by partition. So you could say, okay, which job are running on the work partition? And that will be a shorter list. All right, let me go back to the slides. Oh yeah, something that I didn't show you, because the output of SQ can be quite long. It can be a good idea to use Linux commands such as head and less to just have a look to the output in a more friendly way. And then these are the options that I cover, so the -p and -me. And there are also other useful SQ options that I'm not covering in this module in the interest of time. There are just some references here and more details in our user documentation. This is just the output we had a look at together. Okay, so this we now have a small exercise for you to do, just applying what we just saw with the SQ command. So feel free to play around. We'll just wait for a couple of minutes. I'll let you go through an experiment on Septonics, and then I'm going to come back and discuss the outputs. Okay, so let's give it a go. Let me do it live with you. So the first question is about how many, if you can estimate how many jobs there are currently in the queue on Septonics. And you can do that by piping the output of SQ to the WC command of Linux that will, with the -l options, will tell you the number of lines of the output. So it gives 398. So the first line is the column title. So it means we have 397 jobs running on Septonics as a whole. if we want to get the count just for the copy partition, we can add -p work to SQ and pipe the output again to WC. And we see that out of those 397, 373 are currently queued on the work partitions of most of them. Then the last example was about the copy partition, which is the partition used for data transfers. And we currently have about a dozen of jobs queued there. Some of them are running state, and some of them are pending, waiting to run when the other ones are finished. And these are the outputs. And there is a second bit of exercise for you. When you get to 0.7, this is quite relevant. The 0.7 here asks you to use the command git clone to download this repository from the Pawsey GitHub page. This repository of examples will be used not only on this module, but also in the next ones for today. So if you are keen on trialing all of these examples yourself, I encourage you to git clone the command, this repo now. And for your convenience, I'm going to type it in the chat just to help you. So it's git clone https github.com Pawsey SC Supercomputing user training. And that contains a few subdirectories with a few examples for this module and the next ones. And I think I have to share it with everyone. Here we go. Just giving you a couple of minutes, and then we're going to have a look together. Okay, so let's go through this one together. So this is about giving you an idea of how to monitor a job that you submitted. So let's start again by using this skew-me command. And right now I have no jobs running. So now let me go to my Scratch directory and git clone the repository with the exercises. And now I'm entering the directory and going under job scheduling overview. Now this is a small spoiler from the next module, module 9 on running jobs. So you don't know, we haven't encountered this batch command yet. We are gonna go back to this one in the next module. We're just gonna use it now without any other commands, just to submit the job to the queue. And in fact, now if I go sq-me, I now have a job in the queue, and that's the one I just submitted. And you can tell that because when you use batch to submit a job, you get an output saying submitted batch job, and then a job ID 199401. And in fact, in the output to SQ, the job in the queue is indeed that job ID. And you can see right now, so by default, the job goes to the work partition, and the current status is pending, so it's waiting to run. But the point here I wanted to show you is just how to actually get some meaningful output out of the SQ command for something that you submitted yourself, and that's what we got here. So we're going to go back and discuss in much more detail submitting and monitoring jobs, and actually also setting up jobs in the next module. That's all for this one right now. Okay. So in this module, we talked about what a job scheduler and the job are, some jargon about them, some clusters and partition, some quality of service. We learned how to query the scheduler partitions and job queues using SInfo and SQ, little type of, yeah. And we also shared some best practices on on using the scheduler and the appropriate usage of the login nodes. On the Pawsey online support portal, there is extensive documentation that covers a lot of area in great detail. There is also the possibility to contact the help desk on the user support portal for issues for which you feel you need direct assistance from Pawsey staff. You can become a Pawsey friend, sign up for the newsletter to get the news and event updates from Pawsey. So the module is finished and the session is open for questions.